We begin the next section of Chapter 2 by looking at the differences between compounds and mixtures. To review, compounds are pure substances that are made of two or more elements that are chemically combined in a set ratio. And the example we gave was carbon dioxide. It's important to note that when different elements are chemically combined, they form compounds having properties that are different from those of uncombined elements. So, for example, you have silver, which is a shiny metal. When it is exposed to sulfur, which is a chalky yellow element, it creates silver sulfide, which we commonly refer to as tarnish, which is the blackening on the silver of silverware or jewelry. A mixture is also made of more than one thing, but it's made of two or more substances. That means it could be elements, compounds, or even a combination of both that are together in the same place but are not chemically combined. And this is the difference. A mixture is different than a compound for three major reasons. Number one, in a mixture, substances keep their individual properties. However, in a compound, the substances do not keep their individual properties. In a mixture, they are not combined in a set ratio, whereas in a compound, they are combined in a set ratio. And finally, a mixture is easy or relatively easy to separate its components. A compound can be difficult to separate into its original elements. There are two types of mixtures. There is a heterogeneous mixture and a homogeneous mixture. A heterogeneous mixture is one in which you can actually see the different parts. So a salad is an example of that. In this picture, you can see that I have green lettuce. These might be red tomatoes. Let's call these sunflower seeds. And why not, orange slices. In this mixture, it is heterogeneous because you can see all of the different components that are inside of it. A homogeneous mixture is one in which all of the elements are evenly mixed and cannot be seen individually. Hot chocolate is an example of that. We've mixed the powder and the milk, and while we can separate those things, we don't actually see their different components. A solution is an example of a homogeneous mixture. Air is one example. Sugar water, brass, which is a combination of copper and zinc, are all examples of solutions. I mentioned that one of the differences between compounds and mixtures is that mixtures are, at least relatively, easy to separate into its original components. There are four major ways that this can happen. One way, if we're dealing with things like iron, is by using a magnet. And so you can see here that I drew a picture of a magnet and a picture of metal filings underneath. Things that are magnetic can be pulled out of a mixture of other things that are not by using a magnet. Another thing that can happen is the process of filtering. So just as when making coffee, one puts a coffee filter on top and pours the hot water through, with the ground staying in the filter and the water going into the container, filtering is a process that can be used to separate mixtures. Another method is called distilling. So you can distill a liquid solution, such as salt water. That's what is drawn here in picture number 3. The way that distillation occurs is that you begin with the thing that you're trying to separate. Here we have salt water. If we heat this salt water up, then the salt water begins to boil. As it boils, the water that is in the salt water changes into its water vapor state or its gaseous state. As it rises up, it will follow this tube, which is why the dots are representing the water vapor. And as it moves away from the heat source, what it will do is cool and return to its liquid state, so that you are left ultimately with just the salt on this side and just the pure water on this side. Finally, evaporation. If we took a glass of the same salt water and we put it on the windowsill where there was access to sunlight, over time, the water would heat, turn into its gaseous state, and evaporate, ultimately leaving just the salt at the bottom of the cup. Using this last example of evaporation as an example, it's important to note the concept of conservation of matter. You'll also hear it referred to as the law of conservation of mass. In this law, matter is not created or destroyed in any chemical or physical change. So, in this scenario, with the evaporation of water, while we might not be capturing the water vapor that is evaporating, it is not just disappearing, it is being transferred into the air around. Here, in this example, number 3, a closed system, we would end up with the same mass at the end when we combine the mass of the salt and the pure water as we would when we weighed the mass of the salt water at the beginning. So conservation of mass is a really important topic because we are never creating matter, we are simply rearranging things. So if you look here at this final example, you can see that methane, which is a gas that is flammable, you can see here that there is 1 carbon and there are 4 hydrogen atoms. When those are combined with 2 oxygen molecules, remembering that oxygen that we breathe actually is 2 individual oxygen atoms bonded together, you can see the total of all of these is 1 carbon atom, 4 hydrogen atoms, and 4 oxygen atoms. If we combine those with heat, this is representing a chemical change, which we will learn more about. While they have rearranged to create a carbon dioxide molecule and 2 water molecules, we still have 1 carbon atom, 4 hydrogen atoms, and 4 oxygen atoms. We have conserved the mass of what we began with and still have it at the completion of this chemical reaction.